Recording. All right, welcome back. What we're doing is single variable calculus. This time what we're going to do is we're going to start chapter 1, which is basically going to be real numbers. I have a couple, we'll have to organize this too, but somewhere on there we have a playlist on things you should already know, but you can go look at those videos, or I'm going to do it once again anyways, just for you guys. So what are we going to do? We're going to do the real numbers. So before we start, think of the real numbers. And then this is the symbol we're going to use eventually for it. In your own words, before I start, what is a real number in your own words? And then usually students, when they start doing that, they start giving me examples of, yes, pi is a real number, and 1 is a real number, and 3/2 is a real number, but can you describe the collection of all the real numbers as a unique field? Probably not. It's rhetorical. That's why I've asked it. But what we're going to do is get an intuitive idea of what these numbers are through the journey that we have when we go from our species not knowing what a number is to having all of the real numbers, and then you being forced to know them and do calculus of functions of real numbers and limits. So the idea is just intuitively, just quickly, for our first video, what we're going to do is we're going to view pictorially the real numbers as a set or as a number line is classically how we're going to do this. Long story short, for the number line, pictorial representation, and you have to use Dedekind cuts or Cauchy sequence, equivalence classes of Cauchy sequences, but every point on here has a unique number representation of it. Normally we start off 0, the origin in any of these dimensions. We're going to do this, and then we're going to start marking off integer units, -1, 1, 2, etc. And then once we get weirder numbers, we're going to start trying to fit in. So this makes sense. And then you could, if I asked you where 3 was, you would probably know where 3 was going to end up laying on this, what we call the real number line. But then I give you root 2, and where's root 2 going to be? Well, here's 3/2, and root 2 has to be slightly less than that. We'll find out how to find the decimal expansion, etc. But we're going to use the fractional avatar or the decimal avatar. And that decimal notation is also intuitively what we're going to use to tell you the two kinds of numbers. In that decimal notation, either you're in here, the complement, or they didn't even give it a new name, or you're in Q for quotients of integers or the rationals. So as we go, think about putting the numbers on here. Root 2 is irrational, 3/2 is rational, 1 is an integer, -1 is a negative integer, etc., etc. We're trying to get and build these intuitive classes. What we're going to see is the real numbers are the disjoint union between the rationals and the irrationals, whatever those are, and the most intuitive way of looking at that is by looking at whether it has a repeating or a non-repeating decimal expansion. Let's get into that. You don't even have to pause, I'll just edit out crap after. Yeah. So I still don't know whether I should do that. And doesn't have, yeah, see, the version that Sean doesn't have n in the positive integers. Am I going to? Sure, we'll stick with it. Ah. Where's 0 go? Let's start off the way that they do it. I'll do it differently. The natural numbers are going to be 1, 2, 3, 4, 5. They do it slightly differently. I should look into that, and we should do a video on this now that I'm thinking about it. What I'm using in my head as I do that is either I want to call it Z plus that guy that has that in there, and classically I want to call where I add 0 into those sets, and I'm just musing on this. For axiomatic set theory, what we do is 0 is the empty set, and then 1 is the set with 1 in it, so then 0 becomes a natural number because it starts being the counting, blah, 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 blah. But classically, Peano's axioms, etc., start off with n being this guy. 1 is a positive integer, and then he's the predecessor of everyone else. How do you get these guys? You add 1 to itself, which is what we're going to call the generator. 1 plus 1 plus 1 is 3. 1 plus 1 plus 1 plus 1. There was too many ones in there already, you can see. And so then we start getting, this is what arithmetic and algebra are going to start doing for us. They're going to speed up the process. Instead of adding 1 to 1, instead of having to do that, you can do 2 plus 2, which is that one plus that one, and then you get 4, and then it's going to be shorthand for this. So we'll get the algebra, and we'll use different kinds of arithmetic and binary operations along the way also. So the natural numbers are the whole numbers, the numbers that you're most familiar with. Then what we start doing is, I keep wanting to look over here now, and then I have to look over there. That's all right. Where's my audience? Over here. So what we start doing is we start, who knows what it's going to be. Commerce first, I'm going to guess, in the story. Once you have commerce, not only do I need have enough money for 0 apples, but I still need to eat today. So I say, can I borrow 2 apples or a loaf of bread, Lorenzo? And then I owe him juice because you're not supposed to, but then I owe him, and then we're going to go this way. So the myth is from these positive integers on the real number line, here's 0, and then you mark off a unit length, and then you get the whole numbers. What the myth is going to be is that -1 is just the guy that's the same distance away from 0, and then when you take -1 and add it to 1, you get the nothingness. So we have a way of getting back to nothing if you owe and you're in the red. If you're in the black, then when I take one of the numbers in the black and one of the numbers in the red and I add them to their inverse, they cancel off to give me exactly nothing. So classically, what is that going to be? The next kind of integer is going to be a Z for Zahlen. And this is going to be ellipsis -2, -1, 0, 1, 2, ... You're going to have to chop all of this out. Just bullet points, and then I start ranting on numbers. I like numbers. The next thing we're going to do is quotients, Q, which is going to be ratios of integers. So m over n, such that m is any integer and n is in n. And then what that does is, you can write that different ways, but that says I didn't divide by 0, and you're not allowed to divide by 0. We'll show you, or you can look at one of the other videos why you can't actually divide by 0. Bad. We're on the home stretch. This is like the crash course of 5,000 years in 10 minutes on what we're actually doing here. So the last one we're going to get is the irrationals. What we could ask ourselves is this the Pythagoreans, etc., thought that this was going to be the entirety of the numbers. Every number could be written as the ratio of 2 integers, but then they would find numbers like the square root of 2. And the square root of 2, if you look, it comes from geometry. If you look at unit lengths of a square or a right triangle, that diagonal is what they're going to call the symbol root 2. And what that says is, in the classical theory, root 2 is, or the diagonal of a square is incommensurable to the sides of the square. So incommensurability is the word of the day. There you go. It looks like a German word. Super long incommensurability. So what that means is, if you took this unit length and laid it off, there's no way to take an exact integer amount of 1s and get root 2. There's no, and you could change, and there's no unit length that you think, maybe they thought maybe if I just change it to a unit length and made my unit length smaller, that there would be some way of doing this. And there's no way to commensurate or to measure exactly in unit lengths the diagonal and the side of the square. What that turns into in modern language is the square root of 2 is irrational. And that's what we're going to say about it. And what that says algebraically is root 2 cannot, or not in, that's the symbol for the other one, cannot be written as the ratio of 2 integers. There are no 2 integers that can be written like that. So in in historical contexts, we went from incommensurability of geometric objects to irrational. They didn't even give it a new name. You'd think it would be I for irrational. It's just the complement. If you look at set theory, it's those numbers that are real that weren't rational. And so what is this? This is R, such that R is not written as m over n, where m and n can be any integers. Things that are not the ratio of 2 integers, which it turns out, luckily for us, I'm almost done, kids, I'm almost done. Luckily for us, this will build us an intuitive idea of what R is. So let me erase, and then we'll talk about this in a second. So, long story, I gotta stop saying so. More coffee. I want to do the Ryan Reynolds where it's like Deadpool. It's like, hey, Tim Hortons, you should I don't know. I don't know the word for it either. Sponsor me. I'll take a McDonald's sponsor also. Here's the symbol. It's got a bunch of numbers in it. What we're going to call it is, and then we're going to do it by rote. That means or. So there's a symbol we're going to use. We're going to use this symbol and this symbol a lot in this class. So this is union, and it means or, and this one is intersection, and it means and. And so what we're going to do is domains of functions are eventually going to be all intervals on the domain of one function. If you take f plus g, the domain of f plus g is going to be the domain of f intersect the domain of g. So it has to be everything that's in both of them for intersection. That'll be in the next video. For now, I'm just cheating and saying that why is this a good way of viewing it? Because what this says is, in plain English, every real number is equal to a rational or an irrational. And that's what that shorthand symbolization means in a broken English sentence, which is a sentence fragment still, but close enough. What does this mean for us? What does that mean for us? What that means for us is the rational means that you're going to have an infinite repeating decimal, if and only if, and then the rational means you have infinite non-repeating. Oh, someone important's calling. You can take it, I don't care. Or is it just texting? You're fired. You now get no money compared to what I was giving you before. I know it's rolling, but I'll cut it all out. So what does that really mean? I'll show you in the next video how to do all of this, and then I'll fill you in. But I like to show you the whole forest before we start cutting down trees, because by the time we cut a few trees down, you all think you're lumberjacks, but we weren't trying to become lumberjacks. We're trying to become architects. So we're trying to become architects of the calculus of variation, which means we have to do the instantaneous rate of change or derivative, and then eventually antiderivative of functions of real numbers. So first, let's start off with learning how to, if you're going to build a skyscraper, you're going to probably need some lumber along the way. So we're going to talk about the trees, etc., and how to fell trees. And then you're so happy that you can fell trees, you're like, I'm a lumberjack. But it's like, calm down, you're not. We weren't trying to be lumberjacks. Not that there's anything wrong with that. Sleep all day and work all night. Work all day and you sleep all, wear women's clothing. Have you seen the Monty Python one? It's a good one. It's a good one. Anyways, there's nothing wrong with lumberjacks. What are we actually going to get in here? What this is going to tell us is we're going to have a process. If you have m over n, what we're going to use is long division. And then I can write it as, say, 2/3. One of the ones the Egyptians really liked. That's going to be 0.666 infinite repeating, or what we're going to use is the bar. So the bar is going to tell us that we have an infinite number of sixes. So the bar is playing the same role as the ellipsis, is what that's saying. There should be an equals there. But the ellipsis is the bar. It says that there's infinitely many sixes there, but they repeat. So the repeating pattern is a 6 and it's one long. If we take a different one, I can just make one up. And then what we're going to have to do in reverse, if I make one up and I say 0.023 and I make the bar there, what that tells me is that's the number 0.0232323 ... So the bar tells me that the bar is now only on the 2 and 3, and the 2 and the 3 repeat indefinitely, and there's infinitely many chunks of 2, 3, 2, 3, 2, 3, 2, 3. So how do we go back to go the other way? Here, I'm cheating and telling you we use long division, but I'll remind you how we actually do this process. We're going to put the 3 into the 2, and then we're going to put a bunch of zeros, and then we're going to say how many times they go in there. 0, and then I get a 0, I subtract, I get 2, 20, I get 6, which is 18, and then I get the same remainder, so we can stop, and it's just going to keep giving us 6 is 18, 26, and then we're just going to get, and then we see that we have a pattern, and then we get this. How do we go the other way? This is a nice dirty trick, and I'll show you in the next video, so watch this. But what we're going to do is the clever idea is we're going to call this X, and then we're going to follow Muhammad ibn Musa al-Khwarizmi, and he calls it X, but then I can call this 100X, and I can move the decimal 2 spots. That wasn't enough, so I'm going to move it 3 spots. And then the clever idea is going to be get 2 numbers that have the same repeating part, subtract them from each other, solve for X. I'll show you how to do it in the next video. So what we can show is how to stop saying so when you're doing videos, and then it's so this way. We're making mathematics, we're weaving a tapestry, a sewing tapestry. That's why I say so much. I'll sue you. All right, so I can't not say it. And the hockey players are always I just got off the ice and I'm tired and I'm out of breath, and they were asking me questions about I'm gonna say a lot probably. All right. What we want is what we're going to argue is the rational numbers are a fraction, or what we call the rational number, if and only if you have a repeating pattern. And then we want to ask ourselves, are there numbers that don't have a repeating pattern? And yes, the numbers are the ones, the few that you might know are pi, which is approximately equal to 3.141592 ... or the square root of 2, which is approximately equal to 1.414213 ... or e, which is going to be our favorite guy, which is, that's a 1, I don't know what that was, but that's going to be 2.718281828, etc. Square root of 3, 1.73, I don't know, because you have to memorize these, but we'll find out how. And then we're going to work at, even this is the mystery, and this is why I start off with this section. Do you even know how your calculator is getting these decimals? And this is the decimal expansion of these numbers, and these are all irrational numbers. So what we're going to do in the next video is we're going to show that you're rational if and only if you have a non-repeating expansion. But how does your calculator know that pi is 3.14? How did it get a decimal expansion of an irrational number? And the key to this is using the rational ones to approximate the irrational ones. And the first way they did this was pi. They knew pi was the circumference. So if you take this and call that c and call that d, the ratio of c over d is always pi. And so what they were doing to approximate this is they would inscribe and circumscribe. Don't circumscribe me. You can inscribe me if you want. There's no circumscribing here. Mark's circumscribed, I'm inscribed. I'm gonna guess. Uden. Einstein, probably circumscribed. This is for kids. Shut up. So what they would do is they would take those lengths and they would, that's a circumscribed on the outside, and then inscribe another object. I didn't do it very well, but they would half them. They start with a triangle and double the sides, and then what they would do is say that the circumference had to be shorter or longer than the inside one, the green one, and smaller than the orange one, and then they would get an approximation, and then pi was involved in that ratio, and then they can get the first approximations of what pi is. Pi is, what is it? 3, and they have, well, where's it, Virginia, it's exactly 3. They tried to make a law where it's exactly 3. I'll stop talking now. In the next video, what we're going to do is we're going to flesh out this idea of, we'll do a little bit of set theory so we know how to articulate these sets, but we're going to start looking at the finally rational numbers having a repeating expansion, irrationals have a irrationals having a non-repeating expansion. Let's try that whole fucking thing again. In the next one, we're going to show that the rational numbers have a repeating decimal expansion. Irrational numbers have an infinite non-repeating decimal expansion. We'll show you how to approximate, well, for a few of them, but we're going to use Newton's method and calculus to get at a lot of these answers. But we're going to use, that's why they started calling them that, we're going to use the rational numbers to approximate the irrational so we can get a decimal expansion of these guys. I'll show you how to convert from fractional form via long division into the repeating decimal expansion, and the clever trick, which will be used more than one way in this class, of calling it x, multiplying by appropriate powers, and solving for the variable that we need to get the fractional form from a repeating decimal. And then we'll go and we'll show you the collection of all the different types of numbers, and then we'll start functions. See you next time.